So far, when we dealt with quantum field theory, we had in mind fields and their waves. There was no mention of particles. But then we are made out of quantum fields, and we seem to be made out of particles. So where do the particles come in quantum field theory? So far, it all seemed to be about the amplitudes of quantum fields, much like the amplitudes of the water waves on a lake. So let's see how particles come in. We return now to the Heisenberg picture. And in the Heisenberg picture, to solve a quantum field theory, in particular to solve the quantum field theory of Klein and Gordon, we have to solve the following three problems. We have to ensure the hermiticity of the fields, so that phi dagger is phi at all locations. The same is true for the canonical conjugate momentum field. We have to ensure the canonical commutation relations hold, canonical commutation relations, and the equations of motion, namely that pi dot minus the Laplacian phi plus m squared phi is equal to 0. That's the Klein-Gordon equation, together with the identification of the canonically conjugate momentum field as phi dot. And in order to solve that problem, we simplified it by imposing an infrared regularization. So we assumed that the physics takes place in a huge box of side length L, where we were thinking of gazillions of light years. And we imposed periodic boundary conditions. If we do impose periodic boundary conditions, then we obtain that the Fourier transform becomes, in the box, a Fourier series. And this is the Fourier series expansion, where the expansion functions are e to the power I kx. And the k values cannot take just any values, but they have to be such that the periodic boundary conditions are obeyed. And that is what discretizes the k values. So momentum space becomes discrete. In the project for this course, I suggest you try to do the same thing, but with the box having Dirichlet boundary conditions. This is slightly unusual, but it has a tremendous advantage. And the advantage is that if you use Dirichlet boundary conditions, then the usual Fourier transform becomes a Fourier sine transform with all the sine functions that obey the boundary conditions, that they vanish at the ends of the box. And the sine function is real valued, unlike these plane waves that are complex. And you see, since this has to be real, or self-adjoint, right? Since this has to be real, and these guys are complex, the coefficients have to be complex too. But with the Fourier sine transform that you get with Dirichlet boundary conditions, things are simpler, because now the expansion functions are sinuses. And therefore their coefficients are also real. See, the sine is real, the coefficients are real, so that the fields are real. And that is nice because you get to the mode oscillators directly, not indirectly as we did in the first few lectures. And that is convenient if you want to calculate quantum fluctuations of a field, because you directly get to the mode oscillators and not, you don't need any other change of variable after that anymore. Okay, but so far no particles, right? It's still just fields. We just decomposed the field into its eigenmodes, and that did not lead to the occurrence of anything resembling fields, resembling particles just yet. It's all just fields. So by doing the infrared regularization and putting this, which means putting the system into a box and doing the Fourier transform, the Fourier series transform, we then reformulated our problem in the following way. The equation of motion to solve is this equation of motion, which is a harmonic oscillator equation for complex amplitudes, which is a slight complication, but we've found out that it's not really a serious issue. The commutation relations are these, and we found that the system decomposes now in such a way that the Hamiltonian of the quantum field theory is simply the sum of the Hamiltonians, one Hamiltonian for each mode, where the Hamiltonian for the mode k, and remember k takes only discrete values, where the Hamiltonian for a given mode, characterized by its wave vector k, is given by this. It's pi k dagger pi k plus, and then here we have a phi k dagger k squared plus m squared phi k. So the total Hamiltonian is simply the sum of the Hamiltonians of the individual modes. Remember that each mode is an independent harmonic oscillator, so no wonder that the total energy is simply the sum of the energy of the individual mode oscillators. Still no particles. Still everything seems to be about fields and their amplitudes. But now here comes a crucial observation. And the crucial observation is that for every wave vector, there is an independent harmonic oscillator. I mean, we know that much, but wait for a moment, the crucial observation is coming up. There's an independent harmonic oscillator, and for every wave vector, the frequency of that harmonic oscillator is given by this. Its omega k is square root of k squared plus m squared. You may think, okay, that's just what it is. A mode oscillator, the mode oscillator for wave vector k has frequency omega k. Now what does that mean? It means that for every wave vector there's a harmonic oscillator whose Hamiltonian hk has this spectrum. The spectrum of the Hamiltonian of the mode to wave vector k has this spectrum. The usual harmonic oscillator spectrum, h bar omega half, is the ground state energy. First excited state has 3/2 h bar omega k. The next one is 5/2 omega k. And the spacing between the energy levels is simply h bar omega k. So what this means is that the excitation levels of such a mode oscillator differ by the energy up to a factor of h bar, which we are setting equal to 1 now, up to the energy square root of k squared plus m squared. This formula should look familiar, because this is the energy of a particle of momentum k and mass m, right? So this is where it starts looking a bit like particles getting involved. What we found is that the spacing between the energy levels of the mode oscillators for the mode oscillator for a particular wave vector k is given by this energy, and that's also the energy of a particle that would have wave vector k. We know experimentally that if you create a particle of mass m and momentum vector k, its energy is this. So it looks as if it could be true that if you excite the harmonic oscillator for mode k to the 5th excited state, then on one hand you have to invest 5 times that amount of energy. Maybe you've just created 5 particles of that momentum, right? So this tells us, it's not a proof. This doesn't say that there would ever be a click in a detector that would indicate a particle has been found. No, but what it says is that to excite a harmonic oscillator, a mode oscillator of mode k 5 times costs exactly the same amount of energy as creating 5 particles of that momentum. So that leads us to the hypothesis that to excite a mode oscillator is to describe the creation of so many particles, or to describe the existence of so many particles. At this point, it's a hypothesis, and we have to ask, does this interpretation work? Really, to check whether that interpretation works, we have to go back to the basics. Remember, water waves, we might describe the amplitude as a field phi of x and t, and then we can probe the amplitude of the field anywhere we want by putting a cork into the field and measuring how it goes up and down. With a quantum field, which in the vacuum state typically looks like that, if you measure the field amplitudes, then we can also ask, are there particles? And similarly to putting a cork in there, what we can do with the quantum field is that we can put an atom there. So we place an atom somewhere in the vacuum or somewhere in the quantum field. There may be excitations, right? So these mode oscillators for the production of this particular field, for the production of this particular graph, I took all mode oscillators to be in their ground state. But we can choose the quantum field to be in any state we want. And then we can place an atom there, and we can ask, well, what's the probability for the atom to get excited, for example? Let's say we prepare it in its ground state, and let's say that its first excited state is so much energy away. It takes an amount of energy of, I don't know, E0 or E1 to get the atom excited. And we know what the process is. The atom is in its ground state, and in order to get into the first excited state, it has to absorb a photon of just the right energy. So by placing an atom here in the ground state, and then exposing it to the field, and later on measuring the state of the atom, we are probing whether photons of the right energy were present. See, if the atom is found to be excited when we put it in there in a ground state, then we have reason to believe that it absorbed a photon of that energy. As we will find out, the situation is more subtle than this. But roughly speaking, this is how we can test whether or not there are photons whizzing around, which has put something in there that could absorb them, and then check whether or not they are absorbed. In practice, we'll do it like this. We will describe the quantum field as one quantum system, the atom as another quantum system, and for simplicity, we will describe the atom by first quantization, just the usual quantum mechanics of an atom. Then we have the Hamiltonian of an atom, the Hamiltonian of the quantum field, and we write down an interaction Hamiltonian that describes how the atom sees the quantum field, just the usual electromagnetic interaction in principle. And in principle, you can do this to probe any kind of field, even fermionic ones, or Klein-Gordon fields, or electromagnetic fields, strong fields, and so on. As a matter of principle, you can always do this. And what does one find then? Well, I'm anticipating things here a little bit. We will actually do this, namely write down the Hamiltonian for the atom, write down the Hamiltonian for the quantum field, and the interaction Hamiltonian, and then work out the absorption and emission processes of atoms in a quantum field. We will do that only in lecture 8. But let me tell you already what we will find. We will find that the interpretation of mode oscillators as the interpretation that the excitation of mode oscillators indicate the presence of particles of corresponding energies, that interpretation works somewhat. It works, but it is actually acceleration and curvature dependent. For general relativity, that makes a big difference. We will find that the interpretation is simple. It is as we would expect, namely, you put an atom there, it finds a photon, means it gets excited. That interpretation works in a simple fashion, relatively simple fashion, only in Minkowski space, and only if the atom that we place in there is inertial. The moment we accelerate it, it becomes highly non-trivial. The atom might get excited, even though we might prepare the system in the vacuum state. The atom might find particles present. In fact, it will find particles present if you accelerate it even in the vacuum. In other words, an accelerated atom will not see the vacuum where inertial observers see the vacuum. That is conceptually quite dramatic. It means that what is empty space to one observer is not empty for another. But it's a reasonably good interpretation to say that the excitation of a mode oscillator indicates the presence of particles when the detecting or atom or the detector system, whatever it might be, when the detector system is inertial. Now, conventional particle physics and the quantum field theory lectures that go along with it, in order to understand what's going on at CERN, for example, they gloss over that point because curvature is not so important in Switzerland. And neither is the acceleration of the detectors there. So they're pretty much inertial, and therefore the interpretation of the excitation of mode oscillators as the presence of particles is pretty much okay. So in this case then, what, for example, is the state psi of a quantum field in which we have, just to give an example, three particles of momentum Ka and 7 particles of momentum Kb? How would we write down that state? So the state psi is supposed to be the state with the mode oscillator Ka being in its 3rd excited state, the mode oscillator to momentum Kb to be in its 7th excited state, and all other mode oscillators are supposed to be in their ground state, indicated by Nk equals 0, where N is the excitation level of the oscillators. Explicitly, this means that this state is the tensor product. This is just a convenient way of writing it, but really it's the tensor product of the eigenstate of the harmonic oscillator to mode Ka with excitation level n equals 3. So it's really described by the Hermite function of the 3rd level. Tensor product with the eigenstate of the Kb mode oscillator excited to the 7th state, and the tensor product with the ground state of all the other modes. So the quantum field theoretical state is the tensor product of, one mode oscillator, and all the other mode oscillators' states. And 2 of them excited, and all the others are not. What's the energy of that quantum field theoretical state? Well, when we apply the Hamiltonian of just one mode oscillator onto the state of the quantum field, then it acts non-trivially only on this mode, but it acts as the identity on all of the other mode oscillators, because it's a tensor product structure in the Hilbert space. We should view this really as HK tensor identity, tensor identity, tensor identity, etc. for all the other Hilbert spaces. Then how does it act? Well, if K is chosen to be Ka, then we obtain that eigenvalue times the state of the quantum field, because that's how it's built. If K is chosen to be Kb, then we get this eigenvalue, namely with the 7th eigenstate. And if we choose K to be neither Ka nor Kb, then we just get the energy of the ground state. And then, therefore, what is the energy of the total energy of that state? Well, if we apply the entire Hamiltonian, which is the sum of all of those, onto psi, then it picks up a 3 omega k from the case where the k is Ka, a 7 omega k b from the case where k is Kb, and we pick up a 1/2 omega k from all of the modes. So what this is telling us is that as compared to the ground state, the energy is elevated by this much, which is exactly the energy that it costs to have 3 particles of this kind, 7 particles of that kind. And we have an infinite amount of vacuum energy as well, because we are summing over all modes, over all k, and there are infinitely many of them. And we are summing a 1/2 h bar omega k contribution for all of them. And as k goes to infinity, you may wonder, maybe it's infinitely many terms, but maybe it sums up to something finite. No such luck, because it actually gets worse for larger k. See, for larger values of k, when the decays go to infinity, right? For larger values of k, omega k also increases, because omega k is the square root of k squared plus m squared. So omega k increases, so the higher momentum modes actually contribute even more. And this is very badly divergent here. In non-gravitational physics, it doesn't matter, because that's just a constant. And a constant energy does not contribute to the equations of motion. As we discussed, I think, in the first or second lecture. But of course, in gravitational physics, this sort of thing will be important and represents still a great mystery. You see, it represents a great mystery because we do know that the mode oscillators of, for example, the electromagnetic field really do vacuum fluctuate. They really ought to have a 1/2 h bar omega k. And even if we sum up the 1/2 h bar omega k's just in the range that is experimentally accessible now, let's be conservative and just say we sum them up down to wavelength of a nanometer. That's already way more energy in the vacuum than is consistent with cosmology. So it's very weird. Okay, so this was an example now of a state. Let me put it there again. That's a state where we have 3 particles of momentum Ka and 7 particles of momentum Kb and no other particles. But we could also have linear combinations. For example, we could write down a state of the quantum field where we have 3 particles of momentum Ka or 7 particles of momentum Kb, for example, just for the heck of it. Let's try that. And let's say there is a probability amplitude for having 3 particles of momentum Ka, alpha, and the probability amplitude then for finding 7 particles of momentum Kb is this. It has to be, because we are saying it's either 3 or 7 particles, one of the two, so the probabilities we are legislating to add up to 1. In this case, the state of the quantum field is alpha times the state where all the harmonic oscillators are in their ground state except for the Ka mode, which is threefold excited, plus beta times the state of the quantum field where all the mode oscillators are in their ground state except for the Kb harmonic oscillator, which is sevenfold excited. Of course, this state is meant to be normalized, and so is this one. Notice that this state is not a state of fixed particle number or of fixed energy. Not an energy eigenstate, not a particle number eigenstate. At this point, I should remark that, yeah, we can always take linear combinations, but not necessarily all linear combinations. It turns out that some particle species, some kinds of particles have number conservation. For example, leptons. And leptons are electrons, muons, tau particles, and their neutrinos. And the total number of those guys is always conserved, if you count their antiparticles as having negative particle number. So that means you could not, you could write down such a linear combination, but the idea is that they don't occur in nature. And similarly with baryon number, the number of quarks, if you count antiquarks as having a negative particle number, one moment, also are conserved. In this case, we say that we expect there to be a super selection rule in nature, which does not allow for such linear combinations to arise. Of course, general linear combinations are allowed, but not ones where the particle number is uncertain. Yep?
Doesn't neutrino mixing suggest that neutrino number isn't conserved?
No, if you just mix the species, you see, I'm not saying that the number of these guys is conserved, or the number of those guys. It's the number of any of those.
Okay, so linear combination.
Yeah, the word species is not really the right word, because usually we say that this is a species, that's a species, that's a species. But what I mean is the whole thing is a species. It's just leptons. Yeah, what he was referring to is that neutrinos can change character. Just traveling on their own, they can change character. And that's because their character here, their flavor is these eigenstates are not energy eigenstates, and so that can happen. Okay, so now, as far as that interpretation of mode oscillator excitations representing the presence of particles is concerned, let's just take this interpretation now seriously. That would mean that in order to understand under which circumstances particles get created or annihilated, in order to study the processes for particle creation or particle annihilation, we have to study the processes for harmonic oscillator excitation or de-excitation. So, you see, it's a big step. We're saying that creation of matter or radiation is equivalent to excitation of harmonic oscillators. And we can study that. So let's do this. By which means can harmonic oscillators be excited? There are two basic types, two basic ways in which harmonic oscillators can get excited. I will express it not in terms of fields. I will use the notation of just one harmonic oscillator. It will apply to modes, of course, as well. But just for simplicity, let's call this Q. Q is the elongation of the harmonic oscillator. So we have here the harmonic oscillator equation, and the first way, the first means of exciting a harmonic oscillator that I'd like to discuss is to add a driving force to it. So here we have the harmonic oscillator on its own, and I'm adding a term here which is a driving force. You see, on the right-hand side, you have the force. This is the acceleration. This is basically Newton's second law, right? Here's the acceleration. Here's the force, and I'm adding another time-dependent force to it. And you can visualize this, and here's the experiment for quantum field theory coming in. You can visualize this as a pendulum. Now, a pendulum is not really a harmonic oscillator. I mean, only for small oscillations it is, but it's the best thing I can pull off experimentally here. Okay, so if I move the, okay, so here's the harmonic oscillator, it's just oscillating, right? Now, if I put a force on it, then I'm shifting where the origin of that oscillator is. I can shift the origin of that oscillator by moving my hand left and right, right? Okay, so one way of exciting the harmonic oscillator is with an external driving force, and let's just do this. This thing has its own resonance frequency, which we can see here. If I want to drive it, and I drive it too slowly, if I am way below the resonance frequency, for example, I do this, and you see I'm not actually exciting it. If I go back to standstill, it stays at standstill, right? I have not succeeded in exciting it, even though I have a pretty large amplitude driving force. And the reason is that my driving is below the resonance frequency. If I do the driving way above the resonance frequency, like this, I'm also not succeeding in exciting it. I let it go, it's still not swinging, right? But let's check out what was the resonance frequency. This is it, right? Okay, so if I do it at that frequency, of course, then it will pick up amplitude pretty quickly. In fact, you can calculate that it's proportional to the amount of time that I use it, that I do it. Right? So, and of course, the pendulum becomes nonlinear pretty soon. But you see the phenomenon. Okay, here's the picture for it. Now, there is another way of driving the harmonic oscillator. Much less discussed, but just as important. It may be the reason why we're here. Okay? So it's fundamental for cosmology. The other way of driving a harmonic oscillator is to have a time dependence in its parameters. So you see, generally there is a factor here, and there's a factor there, and you divide by this one, what's left over here is omega squared. So your harmonic oscillator generally has parameters such as the mass and the spring constant. They may be time dependent. What if you have a time dependent spring constant or a time dependent mass? Or in the case of a pendulum, the frequency is determined by the length of the pendulum. What if you change the length of the pendulum? And you don't have that. Imagine it's gone. Instead, your harmonic oscillator equation now is this. No driving force, but the omega is the function of time. Now, let's see. Can we excite our harmonic oscillator this way? So here it is. and I'm putting it through a hole over here, like this, and now I pull on it. Well, it doesn't look like I'm exciting it, am I? I'm not exciting it at all. So was I promising too much? Well, let's try this when it's already swinging. Okay, so now it's already swinging, and now, see what I do? I'm only pulling, but I'm pulling at the right rate, and what's happening is that the amplitude increases. I could also pull in such a way that the amplitude decreases. And it's just off phase. So what we see here is that it's not as easy to excite a harmonic oscillator by making its parameters time dependent, but it is possible, right? Once it is oscillating, then if you pull at the right rate, you can actually excite it more, or in fact, de-excite it too. And that is what is called parametric resonance. It turns out that, well, if you looked at what I did it at twice the frequency of what the resonance was. See that? And that's another difference between the parametric resonance and the usual external driving force resonance. Now, remember the sad picture when I was just pulling at it and the thing was just hanging there and I couldn't excite it? That's because the pendulum at this point was describable pretty much classically. It turns out that when your harmonic oscillator is a quantum harmonic oscillator, then you can excite it even from its ground state parametrically. And that's because a parametric oscillator, just like any harmonic oscillator, right? Any harmonic oscillator in its ground state is not at rest. It always has some oscillations going on. It always has a finite probability of being elsewhere than at the zero energy state. And the parametric driving can pick up on that. It is as if you were to try to excite parametrically a harmonic oscillator that's not completely at rest. Okay, so this phenomenon is also very important in physics, especially in gravitational physics and with accelerations. And it gets even more dramatic. And that's because in gravitational physics, especially in cosmology, the situation can arise that omega squared of t is not only time dependent, but omega squared of t can go negative. It can be so time dependent that this thing changes sign. But when it changes sign, then the situation changes quite a lot. First of all, you don't get oscillations anymore. If you end up with a negative omega squared, that becomes a positive sign, which means that this gets a runaway solution. Think of a pendulum where the pendulum it's not on a string, but it's on an iron bar, and it's upwards, right? So that you have an inverted potential. It now wants to fall. Rather than oscillating this way, it's on its top and it wants to fall. The harmonic oscillator is no longer this way, but the harmonic oscillator's potential is that way now. So that's a runaway solution when this coefficient is positive. Here's a picture for it. And that was the picture for the length changing in time. But does it all happen? Well, all of those cases come up in quantum field theory and therefore in nature. And really what happens in daily life, creation and annihilation of particles at CERN, for example, or just any interactions really, are all described by these phenomena. Even if I just throw this thing around, this physics is behind it. And the reason is that, if you have something that flies, like this, it's in a free motion, it's changing its momentum all the time, right? And that means that different mode oscillators are excited over time. So mode oscillators get excited and de-excited all the time, and when particles crash into each other, not necessarily at an accelerator, but just, you know, billiard balls hitting another, for example. It happens all the time. But on the fundamental level in quantum field theory, here's how it occurs. There's case A. Remember, case A was external driving force. Case B was time-dependent parameters of the harmonic oscillators. Okay, so case A occur whenever there are multiple fields in the Hamiltonian. And in this case, you have a Hamiltonian for one species of field, for example, a Hamiltonian for the electromagnetic field. You will have a Hamiltonian, for example, for electrons. And together this would be quantum electrodynamics, but it's not quite complete. You just have free electrons at this stage and free photons at that stage. But of course they interact with each other. So you will have some interaction Hamiltonian between them. In the simplest case, an interaction Hamiltonian might look like this. In the case of quantum electrodynamics, it's a little bit more complicated. You would have the A field for photons, and then you would have a psi bar psi for the electrons over there. And a gamma mu d mu and things like that. But the overall structure is free Hamiltonian for one kind of particle, free Hamiltonian for another kind of particle, and then some interaction Hamiltonian. Coming back to the harmonic oscillators. This is a bunch of independent mode oscillators. By Fourier, put it into a box, do Fourier transform, Fourier series transform, for example, you get a bunch of independent harmonic oscillators. And here too, a bunch of independent harmonic oscillators. These will be the harmonic oscillators for, let's say, electrons, and these for photons, and they will just oscillate on their own independently of each other. But a term like this is different, because it will turn out that a term like that can be viewed as an external driving force for each of the fields. If you remember how an external driving force looks like, it's the usual harmonic oscillator, and then you have here an external driving force term, and that's what this gives you. If you do the equation, if you calculate the equations of motion, then you will find that this will be a coefficient for that. So you have here equations of motion where this will be a coefficient function for a driving force with the phi, and vice versa. That will be a coefficient function for a driving force with psi. So in other words, the oscillators of this species of particle will be driving the oscillators of that species of particle. And there will be resonance phenomena. And the resonance happens when the energies are just right. In other words, the reason why you need high energetic particles to create high energetic particles is essentially a resonance phenomenon. This is the particle picture that we are heavily employing here to interpret these equations. So we have harmonic oscillators whose excitations describe particles, and then particles crashing into each other is really harmonic oscillators exciting another. But you can also view this in the wave picture. You have waves of quantum field waves of the photonic kind, quantum field waves described here of the electronic type, for example, and then those waves can actually crash into each other and interact with each other. They don't just superimpose another if you have such an interaction term. So there are various ways of looking at this. Harmonic oscillators exciting another through external driving forces, one species representing the external driving force for another species. You can also view it and you can also view it as waves that do not simply linearly superimpose on each other, but that actually interact with each other. On top of this, you can have fields that self-interact. For example, it is thought that the inflaton field is a scalar field that has a potential in its Hamiltonian which is of the form, for example, 5 to the 4th, or maybe likely something a little more complicated. And what that means is that you have the Hamiltonian of a field plus an interaction Hamiltonian, which itself can act as a nonlinearity, as a non-harmonicity. So in other words, the harmonic oscillators are no longer harmonic. If you have a 5 to the 4 interaction in your scalar theory, it's no longer harmonic, and that means that you can describe it as harmonic oscillators that have interactions with each other. That's just self-interaction. Okay, so what happens at CERN you can view as exciting harmonic oscillators, and then the crashing of particles into each other and the creation of new particles is really just various kinds of harmonic oscillators interacting with each other and driving another. Some particles are very short-lived, and you can create them, but then they quickly decay again. And because their creation takes just the right energy, just the right momenta, just the right quantum numbers, and because their creation is a resonance phenomenon, these particles are often also just called resonances, because they are, in this picture, simply brief resonances of harmonic oscillators. Now, let's go to case B, where we don't have a driving force, but instead our harmonic oscillators get parametrically excited. Also, that occurs in nature. So this is the case where the mode oscillators have frequencies omega k which depend on the time. This happens intuitively because Fourier theory was instrumental in getting the independent modes, right? Remember that in position space, we have at every point in space a harmonic oscillator, all right, but these guys are coupled to each other. Only with Fourier theory were we able to get decoupled harmonic oscillators. On a generic curved spacetime, Fourier transformation is not the canonical thing to do. The canonical thing to do is to go to the eigenbases of a canonical operator, such as the Laplace operator, a covariant thing. And as this curvature of space is changing over time, the Laplace operator, which has the metric in it, changes over time. Therefore, the mode decomposition changes over time. And therefore, the coefficients in the mode oscillators' equations of motion change over time. So we do have parametric driving. It's unlikely that we encounter a situation where we have actual resonance, because the universe doesn't tend to actually oscillate much. But if it did, it could also through parametric resonance excite modes. But you don't have to have actual resonance to get excitation. Remember that you don't have, in order to get a harmonic oscillator excited, you don't have to drive it at exactly the resonance frequency. It's just most efficient if you do. And so similarly with the universe, it expands. The parameters of the mode oscillators will be time dependent. And even though that time dependence may be far off from the actual resonance frequencies of certain modes, it will still in part excite those modes. And that would mean particle creation. And we know pretty much how many particles there are in the universe. So we can put a bound on how much of this particle creation can occur or is consistent with observations. Actually, for a while, it used to be thought that it was a viable cosmological theory that the universe has been expanding forever and will be expanding forever, and that the dilution of matter in the universe is made up for by the creation of fresh matter. That was suggested even before it was clear that the expansion itself could accomplish this. But nowadays we know that that's not happening. We can see the evolution of the universe back to 13.8 billion years, and we see really that the universe grew up. It was different billions of years ago than it is now. Okay, so on one hand, we have that the sheer expansion of the universe, even today, produces some parametric driving of the harmonic oscillators, and therefore, in principle, some amount of particle creation, even though it's really minuscule. But it's there. But more dramatic is the phenomenon that very early in the universe, as far as we know, there was a period of almost exponential expansion. And when you have a period of almost exponential expansion, then there is a cosmological horizon, which means that two observers that are more than a horizon apart can no longer communicate because, for example, light signals traveling between them can never catch up with the other guy because space is being created between the two communication partners at a higher rate than light can travel it. That's the particle picture of what the cosmological horizon means. But there's a wave picture too, and that wave picture is dramatic. If the universe, or when the universe is expanding at an accelerated rate, and therefore has a horizon, then for waves, it means that those waves whose wavelengths are larger than the horizon stop oscillating. That is a classical phenomenon already. In a medium that's expanding, you have a horizon and wavelengths that are larger than that horizon. Classical theory says should stop oscillating, should freeze their amplitude. They shouldn't go to zero, they should just freeze their amplitude wherever they are. And the mass of that is described by those runaway harmonic oscillators. They no longer oscillate. You see, if the potential is like this, they oscillate. The potential is like that, they don't oscillate anymore. And there is this runaway solution here. Now you may wonder, what? Are the amplitudes freezing now, or are the amplitudes running off to infinity because of that? Well, they're just freezing. But the thing is that the mass of it, as it will turn out, is the mass of this. And then the amplitude here, just to anticipate this, I mean, we will do this in great detail later on, but the amplitude of a certain variable will indeed go quickly towards infinity. It will explode very much, just like an inverted harmonic oscillator. But that's not the physical field amplitude that does that. To get to the physical field amplitude, you have to divide by the expansion factor of the universe. And it turns out that the physical field then is just freezing. I will do the math of it in all detail. For now, let me just anticipate that it will be exactly the case of inverted harmonic oscillators. And that phenomenon is thought to have been extremely important because this phenomenon is supposed to have meant that quantum fluctuations, which at small scales tend to be very large, at large scales tend to be very small. You know, quantum fluctuations are important in nanotechnology, but they're not important in, building houses or so. Quantum fluctuations tend to be dominant at very small scales, but not at large scales. When the universe had an inflationary period, the cosmological horizon was probably very small, about 10 to the 5 times the Planck length. At these scales, quantum fluctuations were very large. And because there was a horizon, they were frozen. And then as the universe expanded, quasi-exponentially, those frozen large quantum fluctuations made it to cosmological size. So that phenomenon of parametric excitation for an inverted harmonic oscillator is going to be very important. What we also see here is that the particle interpretation goes out of the window, right? I mean, this is not a harmonic oscillator anymore. It's harmonic in a way because it's still the x squared potential or q squared potential, but it's inverted. There is no discrete set of energy levels. There is no way that we could say that there are discrete energy gaps which match the energy needed to create a particle. It's a pure wave phenomenon. We can't interpret that in terms of particles. So gravity can excite mode oscillators without creating particles. Eventually, of course, the harmonic oscillators will have to turn upside down again. I mean, will have to turn the right way again. Then you can talk of particles, and you may have a lot of excitation, may have a lot of particles in that case. All right. So now we have to, since both cases are very important, case A and case B, we'll go through them both. We'll go through case A, mostly just talking about ordinary single harmonic oscillators. But for case B, we'll do the proper thing with gravity and all that. So the case A, external driving of harmonic oscillators will be, just to warm up, basically, and get some experience with creation and annihilation operators. Okay, so case A, particle creation through external driving of mode oscillators. An example of that is the production of photons by an antenna. So for simplicity, in principle we should do that with quantum electrodynamics. But it's unnecessarily complicated. The photons would have vector character, there is a gauge to be fixed and so on. The electrons are fermions, and we'd have to worry about spinors and those things that all those things don't really contribute to the basic understanding of quantum field theory. So let's simplify the picture, and let's describe the electromagnetic field in a simplified way as a Klein-Gordon field. The fact that electromagnetic fields are vector valued and have polarization doesn't really matter at this point. So now let's consider an arbitrary mode of the electromagnetic field, phi k of t. It's the mode oscillator of the electromagnetic field for a particular wave vector, particular plane waves. Now we model the electric current as a given classical field J of x and t, and the electrical current can also be Fourier transformed, and so we obtain a decomposition of the electrical current into jk of t. I hope you see what picture I'm developing here. This thing is going to have a harmonic oscillator, a quantum harmonic oscillator, which will be driven by the current. Right? So we have the electromagnetic field, initially in the vacuum state, and then electrons representing a current shooting up and down the antenna is what drives the electromagnetic field harmonic oscillators. So we will describe the current as classical and the quantum field as quantum theoretical. Later on, lecture 8, we will describe both quantum mechanically. But for now, let's just drive a quantum harmonic oscillator, namely the mode oscillator of an electromagnetic field, through an external classical driving force, just to get started with this. So the idea is that the K-mode oscillator is going to be excited by the JK component of the current. See, if you want to excite an electromagnetic wave of particular wave vector K and therefore corresponding energy, well, it's the current in the antenna that has the same frequency that is going to excite that electromagnetic mode. So in a rough simplification, the electromagnetic field mode K has therefore this Hamiltonian. It's the Hamiltonian of one of the modes as we discussed before. It's the usual 1/2 p squared plus 1/2 omega squared phi squared. And we add now to the Hamiltonian this term. So that if you now calculate the equation of motion, so in particular if you calculate phi dot or pi dot, let's say you calculate pi dot in order to get the Klein-Gordon equation, then the equation of motion for pi dot is I pi dot is equal to the commutator of pi with the Hamiltonian, which would give you the normal thing except there's this extra term. And the commutator of pi with phi gives you the j. So now you have an external driving force of J on the right-hand side. So if you add to the Hamiltonian a term phi times J, then that amounts to adding to the equation of motion of the kth mode oscillator on the right-hand side a driving force of J. So this amounts to the mathematical problem of a harmonic oscillator with the Hamiltonian given by 1/2 p squared plus omega squared half q squared minus jq. It's the same thing, I'm just simplifying the notation a little bit so we don't have to carry around the k indices and so on. So this is the mass of this one single harmonic oscillator, mode oscillator, that's driven by a current, and in practice, as this equation shows, it's the k component of the k Fourier component of the current that's driving the k Fourier component of the field. Okay, so we'll have to decide what picture to use here. Schrödinger picture, Heisenberg picture, interaction picture. Let's see. Remember that for all observables in quantum theory, and that includes first quantization or second quantization, when I say quantum mechanics, I mean Schrödinger non-relativistic quantum mechanics. When I say quantum theory, I mean anything quantum. First quantization, second quantization, it's just quantum theory. So in quantum theory, independently of whether this is first or second quantization, we have that the expectation value of an observable as a function of time t is given by this thing. The state is, let's say, gamma naught. We have the time evolution operator here, and here we have the observable. So in quantum theory, we always have that expectation values can be calculated in this way. And the time evolution operator is obeying this equation here. Initial condition is that it's the identity operator at time t0, where we haven't evolved at all yet. And then the equation of motion is this for the time evolution operator, where this h is the Heisenberg Hamiltonian. Now, how do we get to the Schrödinger picture here? Well, for the Schrödinger picture, this is just a review of things that I'm sure you've seen, but just to be on the same page for sure, here's a quick review. The Schrödinger picture is obtained by putting brackets into this equation. Namely, we bracket this way. Okay, so now we have that this state, gamma of t, is now time dependent because the time evolution operator acts on it. And similarly, that is the Bra version of that ket vector. And the operator does not depend on time at all. See here, neither the operator nor the state depends on time. Everything is in a time evolution operator. And you could argue that this is the natural state of affairs in quantum theory. The time evolution operator does the job of time evolving, and nothing else is time evolving. But if you want the Schrödinger picture, then you bracket in this way that you put the time evolution operator onto the states, and there you go. The states are time dependent, the operators are not, and this is how you calculate the expectation values as a function of time. So here we have the Schrödinger states that evolve in time. Now, what's the dynamics? Well, we can prove, and if you haven't done that calculation yet, please do it. The dynamics is given by the Schrödinger equation, where I d by dt of gamma of t is given by this Hamiltonian acting on that state, and that Hamiltonian is not necessarily the same as the Hamiltonian that we started with, because this is actually the Heisenberg Hamiltonian. So the Hamiltonian that drives the Schrödinger equation is the Schrödinger Hamiltonian, which is obtained by applying the time evolution operator to the left and to the right of the Heisenberg Hamiltonian. And if the Hamiltonian was not time dependent, then it would commute with itself at all times, and therefore you could commute this through there, and you would get a U dagger U is equal to 1, and the Heisenberg Hamiltonian is a Schrödinger Hamiltonian. But in general, that's not the case. If the Hamiltonian is time dependent, you have to make a distinction between the Schrödinger and the Heisenberg Hamiltonians. Equivalently, we can use the Heisenberg picture. We take the equation that I had earlier, and we are now putting a bracket we are now putting brackets differently. Now we bracket this way. And in this case, it's the operators that become time dependent, and they are now called f hat of t, and the states are frozen in time. And the dynamics is given by this, where h is the same h as the one that drove the unitary time evolution. It's this h, the Heisenberg Hamiltonian that we started with. The Heisenberg Hamiltonian, if you remember, is the Hamiltonian in which the operators are time dependent. Okay, so in the Heisenberg picture, the equation of motion of observables is given in this way. That replaces the Schrödinger equation. Later, we will also get to the interaction picture where we bracket in yet a different way, where we partially put the evolution on the states and partially on the operators. I'm assuming you've seen that, but when we come across it, I'll say a few words about it again. Okay, so aspects of the Heisenberg picture. You see, in quantum field theory for cosmology, most of the time we will use the Heisenberg picture. I gave you the Schrödinger picture in the previous lecture just for completeness, but most of the time we will actually use the Heisenberg picture. So in the Heisenberg picture, the state of the system stays the same Hilbert space vector, for example, gamma, right? So because of the way we bracketed, we put all the time evolution onto the operators, and the states don't change. The state will change if we measure. Then we will have this wave function collapse, but until then, the state stays the same. And only the operators change in time. So in the Heisenberg picture, the state of the quantum system stays the same, but the observables, such as the Hamiltonian, such as some observables f hat of t, are generally time-dependent operators in Hilbert space. This has important implications for what will happen in this course. What it means is that the eigenbases and the eigenvalues of observables can depend on time. The eigenbases of the Hamiltonian can depend on time. The eigenvalues of the Hamiltonian can depend on time. And the same for all of the observables. Their eigenbases and spectra can change in time. And in general, we have these equations. We have that the observables are functions of time, and if you want to write down their eigenvector, eigenvalue equations, then the eigenvectors are time dependent, and the eigenvalues also in general will be time dependent. And the same is true for the Hamiltonian. Its eigenvectors and eigenvalues can in general be time dependent. Here's an example. Consider the driven harmonic oscillator, driven by an external force. So let's say it starts out at the time t1 in the nth excited state. So let's say that the state of the quantum system, of the harmonic oscillator, gamma, is the nth energy eigenstate at time t1. Right? So this is a particular Hilbert space vector. And which one is it? Well, it's the one which is the nth eigenstate at time t1. Remember that later in time, the Hamiltonian may be different. And its nth eigenstate may be a different Hilbert space vector. But never mind, our system is still in the state gamma. Right? So we prepared it in that state, and then the Hamiltonian can go and do whatever it wants. But the Hilbert space vector that describes the state of our system is frozen to be gamma by construction. Okay, so at time t1, we solve the eigenvector eigenvalue equation for the Hamiltonian, and we pick out the nth eigenvector, for example. And we say that's the state in which we want to prepare the system. We prepare the system in that state, we call it gamma, and that's it. It will always be gamma, even if the Hamiltonian then changes over time. So gamma stays the state of the system for t larger T1. At later times, the Hamiltonian and its eigenvectors, t not being T1, but t being later than T1, will have, again, eigenvector-eigenvalue equation, and the nth eigenvector will be a different Hilbert space vector. So the En of t is generally not the same eigenvalue as the En was at the time T1, and neither will the eigenvectors coincide. So that means that at time T2, at a later time, at the final time, let's say, we perform a measurement there or so, at time T2, our system is still in the state gamma, which is the nth eigenstate of the system at time T1. But gamma is no longer the nth or any other eigenstate of the Hamiltonian at time T2. So in particular, and that's the case that we'd be most interested in, namely creation of particles out of the vacuum. Assume that a system starts out at time T1 in the lowest energy state, in the vacuum state. It's E0 eigenvector at time T1. And then if the state gamma, which is this state at the ground state at time T1, is not the ground state at time T2, then it means that at the later time T2, the state of the system is no longer the vacuum state, it's no longer the ground state. The harmonic oscillator is no longer in its ground state. I'm emphasizing this because, I mean, in principle, it's a trivial stuff that I'm saying here, but in the Schrödinger picture, it all looks very different. Because in the Schrödinger picture, yes, you prepare the system in the ground state, and then the state evolves over time. So no wonder later on, it may not be in the ground state anymore. In the Heisenberg picture, however, the state is frozen. It's always the same Hilbert space vector. So how do we see excitation? Well, we see it in this subtle way. The state is still the same state. But it's no longer the eigenstate to lowest eigenvalue of the Hamiltonian, because the Hamiltonian has changed. This is how we see excitation in the Heisenberg picture. And we have to wrap our mind around that way of looking at things. So that means this is how it looks like when particles are being created. A state that used to be the ground state is no longer the ground state. Even though it's the same Hilbert space vector, it's no longer the ground state, because the Hamiltonian changed. So now, how do we actually calculate such things? Here's the strategy that we will pursue, and it's totally important because this way of doing things will permeate much of the course. This is still for the external driving force, so it's not exactly the case that we will be most interested in, but almost. I mean, we'll be interested in the parametric excitation, but it's very similar. So remember, the problem of quantum theory is we have to solve the canonical commutational relations at the same time that we have to solve the hermiticity conditions, at the same time that we have to solve the dynamics according to a given Hamiltonian, in this case, harmonic oscillators with a driving force, where the J of t is the driving force, and that induces those Heisenberg equations, which in the case of the harmonic oscillator with the driving force are these equations of motion. P is still Q dot. P dot is the usual backdriving force from the spring constant plus J of t. Please check that if you put this Hamiltonian into that equation of motion for P dot, you get a commutator here with the P of the H, and that picks up that J, get the driving force here. Okay, so we get the system that we wanted to study. A quantum harmonic oscillator driven by a classical driving force, J of t, which could be, electromagnetic field here and a classical current racing up and down the antenna there. In order to solve such a problem, we now introduce A operators, A and A dagger operators. I'm not calling them creation and annihilation operators just yet. The reason is that their relationship to the creation and annihilation of particles is very dubious. It is okay for accelerator physics, but well, even then it's not necessarily okay. I'll show you that the creation operator and the annihilation operators are not generally creating or annihilating particles. So for now, we will do this very carefully, and I think it's important to do this very carefully so that the concepts don't get messed up. So we introduce an operator A of t, which is simply a linear combination of the q and the p. It has some coefficient alpha that we will choose to be real later on, and the coefficient beta that we will choose to be real, but here the imaginary unit. And the overall idea is that instead of calculating the equations of motion for q and the equation of motion for p separately, we just define a variable A of t that has q as its real part and p as its imaginary part. That has q as its self-adjoint part and p as its anti-self-adjoint part. So for now, A of t is just a tool to deal with both simultaneously, with q and p simultaneously. And remember that we are completely free to choose our alpha and beta at our leisure. For now, we make the choice of choosing them real. But what values we choose for that, we are still free to choose whatever we want. It's just a helping auxiliary variable to make solving such a problem a little easier. So how shall we fix our choices of alpha and beta? Remember, we are still completely free to do that. We will make a choice that's convenient. Oh, I should remind you that this really works. It's not just, I mean, when I'm saying that A has as its real part the Q and as its imaginary part the P, yeah, you can really undo this. If you can calculate the A of t, you really can get the Q and the P back with no trouble whatsoever. So imagine that the A of t has been calculated one way or another. Then, as you can easily show, the Q of t is given by this. And you can tell this is just the real part of the A, right? A plus A dagger is just the real part, or the self-adjoint part of it. And P is just the imaginary part of that, right? It's just the A dagger minus A. So really, to solve for Q and P is completely equivalent to solving for A of t. And that's true no matter what numbers we choose for alpha and beta. We are still completely free to choose alpha and beta. We haven't used up that freedom yet. Now, let us calculate the commutator between Q and P, which is set to be IH bar, right? We have no choice in this. Nature told us that it has to be this. And now we express that commutator in terms of the A and the A dagger. So what we find is that when we take the Q and the P expressed in terms of the A and A dagger, or the other way around actually, if we take A and A dagger expressed in terms of the Q and P, then we can calculate what the commutator is between A and A dagger. And it comes out to be 2 alpha beta. At this point, we could leave it as that, and we could say, all right, it just so turns out that the commutator between A and A dagger is 2 alpha beta. But we remember that A and A daggers come up in other contexts where it is convenient to have, so that it is convenient to have a 1 on the right-hand side. Because then we know immediately objects, for example, certain matrices, that have these commutation relations. So what we do is, now we make a choice of convenience. We say, all right, we have 2 parameters to burn, alpha and beta. We can still choose them whichever way we want. we now choose the product of alpha and beta to be 1/2 so that we get a 1 on the right-hand side. In other words, let's say we keep alpha still arbitrary, but we choose beta to be 1/2 alpha. In this case, these are the commutation relations. So we've burned up one of our freedoms for convenience. Not for any physical reason, because the A and A dagger don't do physics just yet. They're just a tool, a mathematical tool, a simplifying variable, right? Okay. So now, in our definition here, here it is. In our definition, we're still free to choose the alpha, but the beta is fixed now, right? Okay. So now, still have one freedom. Now we express the Hamiltonian in terms of the new variable a of t. This is a little messy, right? Remember that the Hamiltonian was given by p squared over 2, and then we had an, it was a p squared over 2, and also an x squared or q squared over 2, right? So here's the Hamiltonian. Here. The Hamiltonian is p squared over 2 and omega squared half, this is a 2, times q minus j times q. The p is the imaginary part of, I mean, it's an a minus a dagger minus a thing, and this is an a plus a dagger thing. So obviously we get here 4 terms, right? Because the p is a plus a dagger, a minus a dagger, 4 terms here, 4 terms there, 2 terms over here. The Hamiltonian explodes, it becomes complicated. Here it is what it is, right? So we get this for the Hamiltonian here. Trouble is that if you write that out, you get terms with a dagger squared and a dagger a and a dagger, and the same disaster happens over here and there. Lots of terms in the Hamiltonian. At this point, we may want to reconsider, did we really want to do this with the a? I mean, it doesn't seem like it's simplifying things, right? However, we still have a joker in our cards. We still have one thing free. We can still choose the alpha whichever way we want. At this point, we realize that if we choose alpha such that it obeys the condition minus alpha squared plus omega squared half over 4 alpha squared equals 0, if we choose our alpha in such a way, then the a dagger squared and the a squared terms of here cancel the a dagger squared and a squared terms of there. See, because the a dagger squared term has a minus 1/2 alpha squared in front of it, and here the a dagger squared terms has this stuff in front of it. So if we choose this plus that to be equal 0, then the squared terms go away, and the same with the a terms, they go away as well. And then we are just left with the mixed terms, with the a dagger a terms. But a dagger a is the same as a dagger up to a constant. In other words, if we now use up our remaining freedom of the variable alpha to ensure this, and the solution to this problem is that if alpha is chosen to be square root of omega half, and correspondingly beta is then chosen 1 over square root of 2 omega, well then the a of t definition becomes this, because that's our alpha now, that's our beta now, and the Hamiltonian simplifies, and it becomes this thing, because the a dagger squared terms and the a squared terms have gone away, and I've used the canonical commutation relations to get rid of the a dagger terms, to get only a dagger a terms. There we go. Now this Hamiltonian is much easier to deal with. That is why we introduced that variable a, because it's so convenient to express the Hamiltonian now in these variables. So at this point, we want to solve for a of t then. Because if you remember, if we have a of t, we get q of t and p of t for free. Just the real and imaginary parts of it. So how do the equations of motion now look like? Well, the Heisenberg equation of motion is that I, f dot is equal to the commutator of f with h. And that's true for a of t as well. I mean, it's true for the real part of it, it's true for the imaginary part of it. It's true for the whole thing because it's linear. So the equation of motion then becomes simply this one. See, that is really simple now. See, because we have only one quadratic term here, a dagger a. That's why it is so simple. Previously, the Hamiltonian of the harmonic oscillator had the p squared term and the q squared term. So the p was coupled to the q was coupled to the p. But in terms of the a and a dagger, it's much simpler because there's only one term in there that has both a and a dagger. So the equation of motion becomes simply this one. And if this term was absent, if there was no driving force, we could immediately write down what the solution is, right? I times the time derivative gives us omega times a of t, but clearly the solution is a at the initial time times an exponential, right? Times exponential e to the I omega t, right? Very easy. In other words, it's this one, right? It's just this term. If there's no driving force, then that must be the solution, right? It's easily seen that this solves that differential equation. And here in this equation here, I've introduced the variable a in. A in is by definition simply the a at the initial time, t equals 0. So it's the ingoing a. It's the a at initial time at t equals 0. Okay, so this, if neglect the driving force for now, this is solving our equation of motion. And once we have this, we're done. We can calculate the p and the q just as the real and the imaginary parts of a of t. With the driving force, the differential equation is not much harder to solve. Here's the solution. This is the solution to it. And I'd like to motivate you to try that yourself. Just plug that solution a of t into that equation to check that it really solves the equation. It's not difficult. You just have to differentiate with respect to t here and there. And you know, if you haven't done that before, do it. So overall, what we have here is, if you just look at the solution, we have the solution without the driving force, as it should be, because without a driving force we get a homogeneous solution, right? And then we have this extra contribution because of the driving force. And what you see is that this extra contribution because of the driving force is effectively the Fourier transform of the driving force over the interval from the start of the driving to the end of the driving t. Because this is like a Fourier factor. That is the force function, j of t. You're integrating the force function over that Fourier factor, e to the I omega t. You see, the factor e to the I omega t, that particular factor you can pull in front. And the factor e to the I omega t prime, together with this, is just the Fourier factor times that. In other words, we see that the impact of the driving force is proportional to the Fourier component of the driving force at the frequency omega, which is the natural frequency of the harmonic oscillator. So in particular, if it weren't present, then we wouldn't have any impact of it. This is only picking out the Fourier coefficient of frequency omega of the driving force. That's resonance. Now, since this is only a driving over finite time, I mean, we later will also let the t go to infinity, but if it's only over finite time, then it's not such a sharp thing because it's not really Fourier transform. It's just a windowed Fourier transform. Therefore, we get some uncertainty in the frequency, time frequency uncertainty principle. Therefore, even if the driving is not exactly at the resonance frequency, we still get some excitation going. I mean, at this point, we can only say there's going to be some impact because it's not going to be zero. So in particular, if the interval of driving is very, very short, then the time frequency principle will kick in. And even if J of t isn't exactly the driving frequency, but is quite different even from the driving frequency, we can still have an impact there. And all of these phenomena will have explicit physical interpretations then in terms of the creation of particles. As we will see in lecture 8, when we will combine the quantum field with a detector system such as the electromagnetic, such as a hydrogen atom. Okay, so let's say, for example, we have a force of finite duration. So let's say J of t is equal to 0 for all t outside a certain time interval. So let's say the driving force acts on this time interval. Before there was no driving force, afterwards there is no driving force. It's an antenna that just is on for a finite amount of time. In this case, let us give this integral here a name. Remember this integral. Let us give this integral here a name. Let's just call it J0. You see, we can integrate up to plus infinity if we want. The only contribution comes from the interval from 0 to capital T, while the force is acting. And so we define J0 to be that integral from 0 to T, while the force is acting. And that thing is going to be some number. So what we find then is that the solution A of t is A in times, which is the A at time t equals 0, times that energy factor for the free evolution for early times. And for time equals 0, this is just identity, as it should be. It's just the solution, the free evolution solution. Then at late times, so when the time t is larger than capital T, so when the driving is already over, then our A of t is simply given by the A in plus J0 times e to the power minus I omega t. That's just another way of writing this thing conveniently. See, this factor here, e to the power minus I omega t, occurs also in here. I omega t minus I omega t. So that's here. And during the driving, while t is in the time interval where the driving was happening, there it's a little more complicated because there we really have to integrate only all the way to the current time. But often in physics, it is convenient to study the initial conditions, then all hell breaks loose, and then when the dust has settled, then we check what the final conditions are. For example, before a black hole forms, then the black hole forms, all sorts of things happen, and then later we check what's the situation now. So similarly here, we have a harmonic oscillator, ground state, for example, or in any case we have the A of t at t equals 0 fixed, A in. And then some driving happens, the J of t does the one thing or the other, but eventually at time capital T, the driving stops. And then we are asking, what's the situation now? What's the aftermath of the excitation that happened? And what we see here is that the A of t evolves like this before the force started acting. The A of t is like this after the force ended acting. And we can easily now extract what the Q of t, the P of t is after the force acted from that solution. And what the implications of all of this are for particle production, for example, photon production by a current in an antenna, we will then do on Friday. Okay, so this was just to indicate how to calculate how our observables are evolving in time, because in the Heisenberg picture, that's what's happening. The state stays the same, but the observables change. Our A of t changes, and the way it changes will be described by a so-called Bogoliubov transformation. Okay? Continue on Friday then.